In this video, we're going to be talking about complex zeros of polynomial functions. And so these are zeros that are complex numbers. And so let's just do a little bit of review. Remember that we use I to denote the square root of -1. And that gives, if we square both sides, we get I squared is equal to -1. And also, you should have learned this back in high school. If you take -1 and raise it to an even power, then you lose the negative sign. You just get 1. And if you take -1 to an odd power, then the negative sign will stay and you get -1. So -1 to an even power is +1. You lose the negative sign. And -1 all to an odd number, you keep the negative sign. So what happens if you want to calculate a large power of I, if you're told to simplify that? Well, we'll have to keep this stuff in mind that we just covered, but also somewhere in high school you should have come by these exponent rules. If not, I'm writing them down here for you to review. So let's look at these, and so I'm going to do them up here. So what I want to do is, if I can rewrite this and use the fact that I squared is equal to -1. Now 26 is an even number, and I can write that as 2 times 13. So this is the same thing as I to the power of 2 times 13. And if I use this rule here, reading it from right to left, I can regroup that like that. Okay, so if I want to write this without the parentheses, this rule says you multiply the powers there. Okay. Now what's inside the parentheses is -1. And then -1 to an odd power is just -1. So I start with that, and simplified, it's just going to be -1. So I to the 26 simplifies as -1. Now let's look at B. Now 57 is not an even number, so I can't solve this the way I did in part A. I have to start out with something, I have to try and rewrite this using an even number. And so what I'm going to do is I'm going to rewrite 57 as 56 plus 1. Okay, so we all agree that 57 is 56 plus 1. Now I'm going to use this rule, okay, reading it from right to left. And using that rule, that's the same as I to the 56th times I to the first power. Now I to the first power is just I. Now I'm going to solve the rest of this by doing what I did in part A. 56 is even. So I can write 56 as 2 times a number, which is 28. And this I out the front is just coming along for the ride. And then now it becomes like part A. So reading that from right to left. And I squared is -1. Now -1 to an even power is just the number 1. So I have 1 times I, which is just I. And so I to the 57th simplifies to just I. And we can confirm that down here. Okay, so I've done that. All the steps that I did up there are in that part. Okay, so continuing on to a new definition. If we have a complex number, then the complex conjugate of it, and we write it with a bar over the top, we keep the same real part, but we changed the sign of the imaginary part. So if I'm looking here, if I want the complex conjugate of 1 plus 7i, that's going to be 1 minus 7i. I just changed the imaginary part symbol. If I want the complex conjugate of negative 2 minus 5i, I only change the sign of the imaginary part. Now, 3i, I can write that in standard form. And so if I take the complex conjugate of 3i, it's the same as taking the complex conjugate of this, 0 plus 3i, and I only change the sign of the imaginary part. And of course, that simplifies to negative 3i. And then finally, if I want to take the complex conjugate of a real number, I'm just going to get the real number, because the complex conjugate, you only change the sign of the imaginary part, and there's no imaginary part to a real number. But let's work it through. Negative 4, I can write that as a complex number, like that. And then the rule for taking a complex conjugate is you change the sign of the imaginary part. And that's the only thing you change. But minus 0 times I is minus 0, which is just 0. Okay. So all of those are done for you there. Now, why are we doing conjugates? We're going to see here. Now, recall, only real zeros will give you an x-intercept. Only real zeros. And also recall that if you have a polynomial of degree n, it will have exactly n zeros if you count any repeating zeros the number of times they occur. So here's a new result, a theorem. If a polynomial f of x, polynomial function with real coefficients, has a complex zero, then its complex conjugate is also a zero. All right. So we're going to use that in these examples. So example 3, find all the zeros of this. So what you would do is you would graph it and look at it in your graphing calculator and see if you can see any x-intercepts, because x-intercepts mean you have a real zero there. Now, when I look at this in the graphing calculator, there is only one x-intercept at 3. And so 3 is a 0. Now, this has degree 3, so there will be exactly 3 zeros. It's possible, how do we get 3 zeros? It's possible that this 3 could be repeated 3 times, because that would fit in. If you count any repeating zeros, the number of times they occur. That could happen. Or we could have 3 as a 0, and then our other 2 zeros are complex, non-trivial complex numbers, in which case they won't give x-intercepts, and they come in conjugate pairs. Now, how do we know which one is which? Well, we're going to need to use synthetic division. Okay, so let me. All right, so I'll do it up here. So we see that 3 is a 0. So what I'm going to do is use synthetic division with the 0 in the box. And if I set this up for synthetic division, I'm going to have that. 4 times the number in the box, then we add and we get 0. 0 times the number in the box, then we add and get 1. 1 times the number in the box, and then we add and get 0. So That's my remainder, which means that 3 is a 0, which we knew. And here is where I get the quotient. So here's the bar. That's my constant coefficient, my coefficient for x, my coefficient for x squared. So I can now write f of x as the divisor, x minus the number in the box, times the quotient, which is going to be 4x squared plus 0x, but I'm not going to write that, plus 1. So if I want to find the zeros, I can clearly see 3 is a 0 here. I need to factor that to get the zeros of that. That will not factor nicely. I can't factor that with whole numbers. So to get the zeros, I know that 3 is a 0. To get the other two zeros, I'm going to use the quadratic formula on that. So that's what I'm fixing to do. So if I'm going to use a quadratic formula, a is equal to 4, b is equal to 0, because it's the coefficient, the number multiplied by x, and there's no x term, and c is equal to 1. So the zeros of that quadratic are going to be negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a, which is going to be negative 0. That just goes away. So plus or minus the square root of negative 16 all over 8. Now don't make the mistake of thinking you can divide that 8 into that 16. You cannot, because the 16 is inside the square root. Now let's bring this plus or minus symbol out the front, and I'm going to bring the negative sign out of here. How do you do that? It turns into an I. So you just can't put in and out a negative sign from a square root willy-nilly. Can't do it. You can't treat a square root like it's a parentheses. It's not. And the square root of 16 is 4. Now I can clean this up. 4/8 is the same thing as 1/2. So I'll have 3 zeros. My 3 zeros are going to be 3, okay, which is it's a real number, so we get an x-intercept. And then here, there is no plus or minus symbol in web work, so you put them in separately. So those are my 3 zeros. Now this is consistent. I have 3 zeros. Only one of them is a real number. So these non-trivial complex numbers do not give me x-intercepts, and they are complex conjugates of each other. So all of that is consistent. Okay, so all of that's in the calculations that we've given here. Okay. All right, now, what if you're given some partial information? Suppose you're told that negative 2 plus 3i is a 0 of this, and then you're told to find all the zeros. Okay, well, I've been given 1 0. So I'm going to write that in my list, unless it tells me not to. And now, for free, I get another 0, because this is a non-trivial complex number, and its complex conjugate will also be a 0. And the complex conjugate, you only change the sign of the number multiplied by I. So negative 2 minus 3i is also a 0. So this has degree 4. There will be exactly 4 zeros, if I count any repeats. Look at the graph, because any x-intercepts will be real zeros. And I have an x-intercept here at negative 5, and I have an x-intercept here at 4. And so negative 5 is a 0, and 4 is a 0, and they can't be repeated because now I have my 4 zeros. And again, this is consistent. Only negative 5 and 4 give me x-intercepts. And my complex ones, they're conjugates of each other, and they do not yield x-intercepts. Now that's really nice when they give you partial information like that. So there's one like this on the web work. So let's look at, I can't remember which one it is. Okay, so they give you one of the zeros here. They give you one of the complex ones, given that that is a root. Root is the same thing as 0. List all the roots. Now this has degree 4. They're going to be 4 zeros. And don't forget to include in this one, it says to include 3 minus 6i in your list. Now for free, you should get the other complex root for free instantly. So I'm not going to tell you what that is, but that will be a complex number. All right, that's very easy and straightforward from the example we just did. And then we'll have 2 real ones. Now, how do you get the real ones? Well, you look at the graph and see where the x-intercepts are. If they're nice whole numbers, you can just fill it in straight away. If at least one of them is a whole number and the other one's not, you can use synthetic division to get the other one. But I'm hoping that they'll be nice integers. Okay, now this one does not want all the roots. What about this one? How many zeros is it going to have? There will be 6 zeros. And they give you 2 of them. And they want to know the other zeros, the other roots. Well, if you know that that's a 0, that gives you straight away its companion, which you should know how to get. And you can write it down straight away. If this is a 0, then that gives you its companion for free straight away without thinking. Now, it said to do not use the given roots in your answer. So there's going to be 6 zeros, but if I don't use the ones I've been given, here we want 4. And so there's going to be 2 others. They will be real numbers. And if they're real zeros or roots, they occur where there's x-intercepts. So you'll need to look at the graph. The graph of what? The graph of this. And you just have to input it very carefully. Okay. Now, that's great if you know, if you've been given this partial information. What happens if you haven't been given any partial information? So let's come back here. Let's look at the same function. So I have the same function, but I haven't been given that information. So suppose we've been asked to find all the zeros of this, but we haven't been given any other information. Well, I would put this in my graphing calculator. And so this is the same function that we're using as example 4. And immediately I would see that I have zeros at -5 and 4. Okay, now there will be 4 zeros in all. The problem is I can't make up the 4 by saying, oh, well, 5 is repeated twice and 4 is repeated twice. Why? Because this crosses through at -5. So it has odd multiplicity. It can't be repeated twice. This crosses through at 4. So it has odd multiplicity. It cannot be repeated twice. So what I've written there in red, it can't happen. So the only other option that we have, you could have maybe the 4 only occurs once and -5 occurs 3 times. because since it crosses through, they have odd multiplicity. That is conceivable. Or -5 only happens once and 4 is repeated 3 times. That is conceivable. Or you could have -5, -4 only occurring once, and your other two are non-trivial complex numbers. Now, how are we going to know which of those cases it is? You're going to have to use synthetic division. Now, what am I going to use on my synthetic division first? Well, I have two integers that I know are zeros, and I'm going to use the one that's not a negative. It doesn't matter. You can choose to start with -5. I'm going to start with the 4. And I'm going to put my one times the number in the box, then we add 9 times the number in the box, and then we add 33 times the number in the box, and then we add and then 65 times the number in the box. Oops. 260. And then we add. So I can now write f of x as, I'll do it up here, the divisor, x minus the number in the box, times the quotient. So here's the bar, that's my constant, my coefficient for x, x squared, and x cubed. Now I need to break this one down. And what am I going to put in the box? Well, I've used up the 4, so let's put a -5. Because if it's a 0 for the big one, and I haven't used it in synthetic division, it'll be a 0 for this one too. So that's what I'm going to do. I'm going to use -5 in synthetic division with this cubic. So I'm going to have 1, 9, 33, and I'm expecting to get 0 as a remainder. If I don't, I've made a big mistake somewhere. 1 times the number in the box, then we add 4 times the number in the box, and then we add, and 13 times the number in the box, and then we add. So now I can further break this down. So this x minus 4 is coming along for the ride. Then x minus the number in the box, x minus -5, then times the quotient. And here's the bar. There's my constant, my coefficient for x, my coefficient for x squared. Now I can try and factor this using the trick, but it doesn't work. So this does not factor over the integers. I want to find the zeros. Of course, we have 4 and -5 are zeros. What are the zeros of that? Use the quadratic formula. Okay. So I'm going to use the quadratic formula. And a is equal to 1, b is equal to 4, and c is equal to 13. So my remaining zeros are going to be -b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. Okay, so this is going to give me -4 plus or minus 16 minus 4 times 13. So okay, so this is going to be plus or minus negative 36 all over 2, which is going to be negative 4 plus or minus, the square root of negative 36 is 6i. And now I can divide this up, negative 4 halves plus or minus 6i over 2, and that will simplify. My zeros are going to be 4, negative 5. Then down here, that's going to be negative 2 plus or minus 3i. Now, you can't put plus or minus into web work, so you're going to have to write them separately. So one is negative 2 plus 3i, and the other is with the negative sign, negative 2 minus 3i. And I get the same zeros, the same result. So I had to do a bit more work because I didn't have any information to start with. So it's really helpful when you're told what the zeros are. All right, so here I said you had to use synthetic division with 4 in the box to get this factorization. Then we use synthetic division on this smaller one with negative 5 in the box to get that factorization. And these are how you would type them up in web work. Okay, so there is no plus or minus symbol in web work. You have to type them in separately. Okay, and then finally find all of the zeros to that. Okay, well, again, this has degree 5, so there are going to be 5 zeros. Okay. Now, before you do anything else, look and see if they have anything in common, and they do. They all have an x term in common. They have at most an x in common. You can factor it out. So I can find a 0. What will make this 0 if x itself is 0? So 0 is a 0. And what's inside here is what we've done on our previous example, and we know the zeros for that one. So you thought this one was going to be really long, but it's not. So I get this one in the previous examples yields that 0, and then just by factorizing, I was able to find out what the other 0 was. All right, and again, you type them in separated with a comma. Okay, so that finishes this video, and there should be you should be able to do your web work now that covers that.